it's my pleasure to present you Jan Arms. He is a professor at the Gran Sasso Science Institute, and most of all, he was also my supervisor. He is working in gravitational wave field since 25 years almost, and his expertise are kind of various, mostly on seismic and gravity noise, and he is also coordinating the instrumental science board of the Einstein Telescope, and he worked in the gravitational wave interferometer LIGO, then Virgo, and now he is also driving this new experiment using the moon as a gravitational wave detector, but he will tell you about this now, so enjoy the talk.
Thank you, Francesca. I think this should work. Okay. Yeah, thank you first for this kind invitation to Genova. It's my first time in this building, at least, and you have like an enormous space for physics. I'm really impressed. Jesus' eye is way smaller. Yeah, so I am from Germany, born in Germany, close to Hanover, and then at some point I left, spent some years and came to Italy. That's how it happens. Now I'm at GSSI, and I will today tell you a bit about the Lunar Gravitational-wave Antenna, which is a concept that we proposed back in 2020 to detect gravitational waves. So maybe the first question that some people might have is, well, what is that? But the other question might be, do we need it? Because we have, when you think about the future of gravitational wave detection, you might think of Einstein Telescope, of the space mission LISA. We have the pulsar timing arrays, and so on. So do we need more gravitational wave detectors? So let me get to that point first to give you a little bit the overview. Okay. So essentially, the important story here is about frequency. Today already, we have instruments in place that attempt at least, or have already, detected gravitational waves from like frequencies which are close to, you know, I mean, of course, for us humans, without any, so essentially static signals, 10 to the minus 16 hertz, up to a few thousand hertz. And so we have here, for example, the probes of the cosmic microwave background. So you know, people are studying the polarizations and try to find the B modes and associate them with imprints left by gravitational waves in the early universe. It goes then to the pulsar timing arrays, which are essentially formed by radio telescopes in combination with pulsars, so that we essentially receive regular pulses from these sources, which we observe over long periods of time, and then try to find little modulations in the arrival times that we could connect to the passage of gravitational waves in our galaxies. And so here we are talking essentially about nanohertz signals. And then we have now the approved space detector LISA. So it is supposed to be launched in 2035. It's an ESA mission with a NASA contribution. And this is going to measure maybe, you know, at millihertz below and a bit above millihertz, so in that range of frequencies. And then we come to the terrestrial detectors. Of course, you know Virgo very well, LIGO. And well, now back to the question, is this enough? The point is simply each of these observatories' methods of observing gravitational waves targets different sources and different signs. And each gap is potentially interesting to us to observe. So gap between pulsar timing arrays and LISA, or between LISA and the current terrestrial detectors. We would like to cover all of it, very similar to what is happening in the electromagnetic band as well. And so we, you know, in the field, there have been many studies of where we actually would like to place the next detectors. And it turns out the most important of these bands is between the LISA detector and the terrestrial detectors, between about, let's say, a few tenths of millihertz to a few hertz. So it is a band that we are not able to cover with planned detectors. And it's technologically, it turns out to be the most challenging band to cover. And well, we propose wave antenna to find signals exactly in this band. Okay, so I would say more about the science and so on later on. Let me, okay. So some of you might know this video. This was published after the first detection by the LIGO detectors of the binary black hole. So here you see the binary black hole. You see like the space-time disturbance that propagates out. Eventually, it comes to the merger and the maximum of the emission. And so that propagates out into the universe without really being affected much by the matter in between. That's not entirely true. So do study, of course, lensing effects, for example, on gravitational waves. But let's say these effects are much rarer and less impactful than what we know from things that can happen on the electromagnetic side. And then once these waves arrive at Earth, for example, they produce vibrations of the Earth. So the Earth is kind of ringing up like a bell. So you can think of this as like a hammer that knocks on the Earth, and then you create a kind of vibration. That depends also on how exactly, what exactly the waveform is of space-time that is passing through here. And this idea that you can use an elastic body, essentially, to detect gravitational waves is quite old. It was even well, I'm not sure really how this happened in the very early days, because also the laser interferometric idea is very old. But let's say, historically, the experimental effort started mostly with what we call the resonant bar detectors, which were invented by Joe Weber in the US, in Maryland. And so they started to build these lab-size experiments where they had aluminum bars of high quality, which and then they looked for vibrations of these aluminum bars excited by gravitational waves. Now that same idea also works for much larger objects like Earth and Moon. Okay. So this is then what we proposed in 2020. We want to deploy essentially a network of an array of seismic sensors. You can think of it as the transducers of an antenna, where the moon itself is the antenna, and these are our transducers that take the response of the moon and turn it into a signal that we can read. And so essentially, when a gravitational wave passes by, it induces a quadrupolar vibration of the moon. And this happens at all frequencies. Now, there are some frequencies where the response of the moon will be enhanced. These are the normal mode frequencies. So these are associated with specific quadrupolar vibration modes of the moon. And so there you can find a much stronger response. Generally, though, the response happens at all frequencies. Now, this concept, I will come to some of the details now, but let me first refer to another experiment that took place a long time ago, which had the same idea, but it didn't work, and also, you know, technology was not so advanced yet. It was the lunar surface gravimeter that was deployed on the moon by the crew of the Apollo 17 mission. That was 1972, the last Apollo mission. And so this instrument had as prime science for the detection of gravitational waves. So Joe Weber, the same person who invented the resonant bar detectors for the laboratories, he also understood, of course, the moon does the same thing. He also knew already from some seismic data from previous Apollo missions that the moon is extremely quiet. And now that is a very important point. If you want to detect vibrations like that, you can now imagine when they are produced by gravitational waves, they will be very, very, very weak, low amplitude. So we are talking about something depending on the frequency of you know, near picometer or something like that. So really tiny displacements. So you need a very quiet place to find those, because any other disturbance, like you know, earthquakes, atmospheric perturbations, human beings perturbing your signals, or oceans, all of that makes that idea kind of you know, difficult to do on Earth, for example. We tried. We used thousands of seismometers, and we did our very best LIGO Virgo pipelines with these sensors. And we tried to find gravitational waves with that idea on Earth, but it's not possible. You come within 2 orders of magnitude to a detection, but not quite. So this idea works if you go then to a much quieter place. And I will show later how quiet it really is on the moon. Now, the idea is old. It didn't work because the sensor here was simply not good enough, apart from the fact that it had a design flaw. So the company, Lacoste and Romberg, that made this sensor opposed certain tests, because these tests would have revealed certain technological details to the scientific team, and they didn't want the scientific team to know these details. And so they decided against certain tests. And these tests actually are the reason why it didn't work, because there was a miscalculation in the end in the balancing mechanism of mechanics connected to the change in gravity. So the moon has less gravity, and somehow the balancing mechanism didn't have enough range to actually work in the end on the moon. So this is also an example that you cannot work like this with these important experiments. The testing must be fully open. In any case, even if it had worked, they wouldn't have detected gravitational waves. The sensitivity was not good enough. So now, very briefly, about the key aspects of LGWA. So instead of 1 station, 4 stations. Why that? Even though we know that the moon is extremely quiet, we still believe that at the end of the day, there will be a seismic background that will limit our sensitivity to detect these fluctuations, the displacements. So what we need is essentially an array of sensors where we can then distinguish with data between a seismic background event and a gravity. So that's the reason why we have 4 instead of 1 station. Then the other really important part, which makes it very complicated, is that we want to deploy this in what is called a permanently shadowed region. So these are very unique regions in our solar system. There are very few of them, and only on 2 or 3 planetary bodies. So essentially, the moon has a rotation axis which is almost perpendicular to its orbit around the sun. So that means like the sunlight always comes at the same angle almost, grazing angle at the poles of the moon. And so you can imagine if you have a crater now, that there are parts of the surface which never get sunlight. And so these become very cold. So they are always below 100, continuously below 100 Kelvin. Some points are continuously below 40 Kelvin, so very cold. And why is that important for us? There's directly a gain for the sensitivity of our instrumentation, but far more important is the following. If you have temperature changes, then your payload can respond to it. It can deform, it can expand, contract. The same can happen with the lander. The same happens with the ground as well. So any temperature change causes noise in our measurement, and it is something that every gravitational wave detector has to fight with. It's Virgo is introducing a temperature stabilization in all its buildings to not have this problem. In LISA, they have a huge issue with the telescopes, so they have to somehow make sure that the telescopes that send out the big laser beams to the other satellites, that they deform too much under temperature variations connected with fluctuations of the light of the sun, and so on and so forth. Here is the same thing. We have to make sure that we don't have the full temperature change on the moon, because anywhere on the surface of the moon, between light and day, the temperature varies between 100 Kelvin to 400 Kelvin. And so this is a very quick change that happens between, over a few days during sunrise and sunset on the moon. And that would just completely invalidate the whole idea. So for that reason, we deploy in these permanently shadowed regions to gain temperature stability. That's the main point. And this will remove a lot of noise from our measurement. So that's the big picture. And now let's get to some of the details. So first, I will talk mostly about the science now, a bit more about the instrumentation as well, but you can imagine now the moon itself becomes our test mass. So when we talk about test masses, then in the case of LISA and Virgo, it's typically like mirrors out of fused silica or a gold platinum cube or something like that. These are the test masses. Now, for LGWA, the test mass is the moon. And so when we want to do that kind of detection, we have to understand the moon really in detail. And that means that to do LGWA, you have to do a lot of lunar science. You have to understand its internal structure. You have to understand its geophysical environment. So these are all very important topics. And then, of course, covering a new frequency band with respect to gravitational wave observations gives us many new sources which you cannot see in the future with terrestrial detectors or with LISA. Okay, so let's look a bit at this. The first thing, the moon is extremely quiet. So here you see a histogram of seismic spectra that come from Apollo 16, from the station. And so you see here meters per square root of hertz, and here 0.121 hertz. And so what you see essentially is that, there's a huge variation. Blue means it's a kind of a measurement that happens rarely. Red means that this is what you see most of the time in your data, this kind of spectrum. Now, you can compare this first of all to these traces here, which mark the absolute minimum of vibration that you can ever observe on Earth. There is an absolute minimum because there's a certain energy put at each frequency on Earth because of different effects. Be it, I mean, in this band, most importantly, it's the oceanic perturbations, the oceanic microseisms, which output most of the energy into the seismic field. And so you have this minimum, and you will never observe something weaker than this minimum anywhere on Earth. So you see already that the Apollo mission here, most of the time, measured something which was 2 orders of magnitude quieter than this absolute minimum. And now you might ask, what is this? Well, this is the instrument noise of the seismometer. So in reality, the seismometer didn't see the actual seismic background. It saw its own measurement noise all the time, most of the time. Occasionally, there were moonquakes and so on that, you know, elevated the level of the signal in the seismometer. But what we can say with respect to the continuous seismic background, which is really the thing that would limit our sensitivity, this continuous seismic background is below that level. And we don't know how far it is lower than this level here. Some models, and now ask yourself, okay, what would produce this seismic background on the moon? So there are moonquakes, but they are rare and they're much weaker. The origin of a continuous seismic background might be connected, for example, to meteoroid impacts, which come in at all, you know, at the full mass range. There's no atmosphere to burn them, so they all get to the surface of the moon. So the collection of all of these meteoroid impacts is probably what forms the continuous seismic background on the moon. And so people model that because we know more or less the flux of and the mass distribution of these small meteoroids. And the prediction is that the seismic background is maybe at a few tenths of femtometer per square root of Hertz. And of course, that means we are now talking about 6, 7 orders of magnitude difference in amplitude of the seismic background compared to Earth. And that is what enables really all the great science that we want to do. Okay, just to say, you know, we know quite a bit about the seismic, about the meteoroid impacts. On the other hand, there are many things that we still have to understand. For example, the impact is not uniform over the surface. There's actually evidence that the impact rate at the poles is even lower because it is like, you know, moon is like a vacuum cleaner that takes a little bit the dust off from the orbital plane. And so most of the impacts are near the equatorial region of the moon, and much less comes on the poles. And this is good news, so that has to be studied because this is good news because since we want to go to the poles, we can expect that all the predictions of the seismic background from the meteoroids might be actually much less at the polar regions than you know, the values that we are using today. So that would be important to understand. And then other things, I will, you know, explain this a little bit better later, but we are also very concerned about the magnetic fluctuations at the lunar surface because essentially our sensors have a magnetic susceptibility that we need for actuation, and so we can couple to the external magnetic fluctuations. So we also have to understand exactly what causes magnetic fluctuations in the sweet frequency band between 0.1 and 1 Hertz, where we want to do most of our science. So you see already we are connecting, you know, to a lot of lunar science and geophysics on the lunar surface with our concept. Okay. Now, the big question, and that's where we have like the really important question marks at the moment when it comes to what we can really do at the end of the day with that detector, is connected to the lunar internal structure. We know a bit from studies during the Apollo era where all the seismic data was evaluated to infer essentially a model of the internal structure. But it turns out that there are many question marks. We don't really know, for example, for sure if there is a liquid core, or maybe there's the moon could even be partially hollow. So people have all kinds of theories because the seismic data was really not of the quality that we need to make very good inference of the internal structure. But for us, this is really important to be able to accurately calculate the amplitude of the moon in response to a passing gravitational wave. So when we want to calibrate our data, then this will be limited by how well we know the internal structure of the moon. Now, you might also think like, is that not a showstopper? I mean, this is geology. I mean, how precise can you ever be with geology? Now, there are tricks. Essentially, imagine that you know exactly the amplitude of a space-time fluctuation. And now you observe the response of the moon to that signal. Now then you can calculate the relation between the two, and you have now the factor that you use later on to calibrate any other data that you have. How can you ever get into the situation? Well, you can if that same source is observed later or before that with other detectors. LISA and Einstein Telescope will have very well calibrated data, and so they can tell us essentially, look, we observe now a Newton star binary. It has just merged with Einstein Telescope. We have observed it. This is the amplitude of the space-time fluctuation. Now, 3 months ago, it was in your band with that amplitude. Now look at your data, and so that is, for us, a way to calibrate very precisely our data. What that means essentially is that all the signals that are so well calibrated, we can use to make a tomography of the internal structure of the moon. So that would be the first practical application of gravitational waves. We will use it as a tomography to provide the internal structure of the moon. That would be the first case of high precision geology in history, I guess. So in any case, this is our plan. Of course, you can also arrive at calibration in different ways. You could essentially, if you for years observe moonquakes, you will learn more and more about the internal structure of the moon. And so you can over time refine, in any case, your understanding of the internal structure. But if you want to get a 1% calibration of your data accuracy, then you rely on this kind of multi-band scenario. Okay. Now, one of the complications is that it's not only about this large-scale structure, unfortunately, and deep structure of the moon, it is also about what happens closer to the deployment site. And so then it becomes messy. The moon has not like a very, let's say, compactified soil. It is this regolith, and it's fractured. There were big meteoroid impacts in the past. So what really, all these details might matter in the end to understand the geology precisely and the response of the moon to gravitational waves. And so here are just some waveforms to show what was observed. Essentially, these are signals, in time of moonquakes with an Apollo seismometer, and you see that essentially that the waveforms are very, almost like a diffuse signal, almost random, even though the source is just like an impact, for example. But then the signal that you observe is like this kind of this random forest of noise that comes and then fades away. So that doesn't, if you look at this, you might think, okay, this will get really hard to calibrate your gravitational wave data. But okay, honestly, we don't really understand this problem very well. So now, gravitational wave science. I told you already, okay, the important role of LGWA would be that it is between LISA and, let's say, Einstein Telescope, okay, in frequency. And so there are certain sources that you can observe only there. Most of this is connected to white dwarfs, because white dwarfs you can detect also with LISA, but this is happening well before they merge. So essentially, LISA will observe double white dwarfs that don't change in frequency or very little. So these are just like very early in spiral waveforms, near monochromatic signals. So what LISA can do with white dwarf binaries is make a census of masses, locations, numbers, and so on. But they cannot see the merger. The merger of white dwarf binaries and things that might happen before the merger, like tidal disruption and all of these interesting phenomena, they would appear in the decihertz band of LGWA. So that's the detector that you want to use to get to the more exciting white dwarf physics. Then measurements in this frequency band would also be optimized to observe certain masses of double of binary black holes. We call them intermediate mass black holes of like around 1,000 solar masses. And so LGWA would see them out to greater distance than LISA and Einstein Telescope. Okay, let's look at some of this. In terms of sensitivity curves, I hope you are kind of familiar with these plots. So between 0.1 millihertz and a few thousand hertz, you see like the full spectrum here. You see the targeted LISA sensitivity. the targeted Einstein Telescope sensitivity, Cosmic Explorer, the proposed American next generation detector. And here we would land more or less with LGWA. And so you see IMBH, this intermediate mass black holes, you know, these binaries that would go through the band of LGWA and then merge at low frequencies inside the Einstein Telescope band, for example. Or a Newton star binary could stay here for months in the band of LGWA and then eventually merge. And so you see that this is kind of an interesting situation. Supermassive black hole binaries, they would be seen with very high signal-to-noise ratio by LISA, but then the merger might also appear in LGWA data. So this is a kind of connection to the other detectors that you have to be aware of. Now, this is now what we call detection horizons. Essentially, depending on the total mass of the binary, redshift. So, for example, this is very hard to see, but the Einstein Telescope, well, it has a peak horizon at redshift of 100 for like 20, 30 solar mass black hole binaries, while LGWA has a peak horizon of maybe 50 redshift for these intermediate mass black hole binaries, and LISA has like an enormous horizon for, you know, close to 1 million solar masses or yeah, like 100,000 solar masses, okay? So each detector has an optimal mass for the high redshift detection. And so we would fit right between here. And so you can see 1,000 solar masses, you know, with LISA and ET, you would maybe get to redshift 7. And these are really ideal conditions. So the source would have to be optimally oriented and located in the sky to see it out to that distance. So it would really be an important impact that LGWA would make also for these binary black holes. And so studying intermediate mass black hole binaries at these high redshifts is an important part of understanding the full black hole population in our universe. You might know from JWST that they are kind of putting stress on all of our models how big black holes formed so quickly in our universe. And so the mechanism is not perfectly clear how this is even possible. And so intermediate mass black holes could play a role. Exactly how things happen in the early universe today, however, nobody knows. There are some models, but understanding them really requires observing the full range of masses here in the very early universe. Okay. Now, the other thing which is interesting in this plot, I'm adding a little bit of a detail. With respect to LGWA, these signal spectra, they look a little bit more complicated. So there's the merger, and then there's the in-spiral phase, and then it gets to the merger, and then it ceases. But here, for some of the signals, you see that the signal has these weird wiggles at an earlier point of the in-spiral. And so where does this come from? This comes from the fact that the moon is rotating. And so the signal that we observe with our detector is modulated in time. In phase, because the moon is also moving around the Earth and the Earth moves around the sun, but also in amplitude because the orientation of our seismometers are changing with time with respect to the source location. So these wiggles are connected to the motion of the moon. Now it turns out that because of this effect, we can, just using LGWA, triangulate the source very, very precisely. So what we do today with LIGO Virgo, using 3 detectors operating at once to take the time, the time shifts between the arrivals to triangulate the source, we can do alone with 1 detector if you just observe that source long enough and you see these variations in phase and amplitude connected to the motion of the moon. And that allows you then to triangulate very, very precisely. We're talking here about sub-square degree localization. So now, for example, if you observe a Newton star binary for 1 month, you would already be kind of sub-square degree with the sky localization. When the BNS, the binary Newton star, leaves the LGWA observation band, it is the sky localization area is shrunk to this little spot in the sky. Now, what does it mean? If we can do that, we can tell 2 things to our earthly friends. We will say, first, there will be a Newton star merger in 3 months, 6 days, 2 hours, 5 seconds, and so on, and you stay put. Something is coming. the other thing is we will tell them exactly where this is going to occur. Now, that means for any electromagnetic observatory that is targeting the weak electromagnetic signals like a kilonova produced by these mergers, they can point their telescopes there in advance and wait for it. And they can see the full evolution of the electromagnetic signal instead of missing like hours, as it happened with 170817, where we, I think, started to observe the kilonova after 11 hours or something like that. And they are really, they really would like to catch a much earlier part of that signal. So that would be also a huge contribution. Just a caveat. So we would probably see around 1 of these BNS per year with LGWA. So it's not so many, but okay, still. Now, the other part, and that's where really a lot of science would be done with LGWA, is concerns the white dwarf mergers. So with LISA, you have a horizon for double white dwarfs of close to 2 megaparsec. Now that means it's us and the Magellanic Clouds, and that's basically it. You don't even get to the Andromeda Galaxy, okay? So LISA doesn't see essentially anything outside our galaxy except for what is like orbiting around us directly. So the Magellanic Clouds. So that is a strong limitation. Of course, LISA will do an amazing census of the galactic population, but that's basically where we will be stuck. With the decihertz detector, you can increase the range by a lot. Now that depends a little bit on the details of what happens at the very end of these signals, like how exactly the merger happens, how big the white dwarfs really are, and so on and so forth. But you can get to maybe 10, 20 megaparsec. At this point, you have a larger number of galaxies already in your observation volume. And that means you can really hope to see maybe tens, maybe a few hundred white dwarf mergers per year. Now that would be amazing because white dwarfs are really having an important role in many other things like cosmology. For example, you might know of this question, what is the progenitor of a supernova type 1a? So we don't know for sure today if it is a single white dwarf accreting matter from a companion star, or if it's a double white dwarf doing some kind of merger. This thing here was ruled out earlier in the past because they suspected that the matter distribution that is spilled out by this event should not have a high symmetry because you have two objects that collide, so you would expect maybe some kind of dipole deformation, while what you really observe are near spherical kind of matter outflows from these points. And so that was kind of speaking against it. But then this model kind of, and this pointed to that model here, but then this model here has its own problems. And so today, really, there's no consensus in the community what the story really is. So one would have to, one could, of course, answer that question by observing a white dwarf binary merging, and then hopefully from that same location, the sky, see the supernova type 1a. Also, there are some question marks. We don't know for sure how long it takes after the merger that we see with gravitational waves until there's an electromagnetic signal that we can see, which we identify as supernova type 1a. There is potentially a long time delay. Some people say it could even be hundreds of years between the merger and the supernova type 1a. We don't really know because it might be that the merger creates a metastable object that might, I don't know what happens. I'm not really the expert for that, but there could be long time delays. And so the association of a supernova type 1a with a merger of two white dwarfs might not be so clear, even though most of the simulations, the numerical simulations that we have today tell us, it should have a prompt electromagnetic signal as well. But this is to be seen. And as you might also know, supernova type 1a play an important role in cosmology because they are part of the cosmological distance ladder. And there are some obvious issues that everybody knows of. There's this, the Hubble constant problem that Planck and astrophysics doesn't really match. So we hope, with these observations that you could learn more about the supernova type 1a and maybe get to the bottom of what causes the discrepancy. Okay. Now, very briefly, again, about explosion. Strange enough, with LGWA, you could also hope to observe core collapse supernova. Now, for people who have heard about this before in gravitational wave observations, this is considered a high frequency signal where most of the energy is maybe output at, you know, 1,000 hertz or something like that. Now it turns out there is a low frequency signal coming together with it, which is called the memory effect. So essentially, when, you know, we almost never talk about this, when you have a black hole binary merging, and you see the waveform, what happens is that together with the oscillation, there's a step happening in space-time. The space-time settles at a new, let's say, metric deformation which lasts. So you have an oscillation, on top of it, a step function. And that step function is connected to the overall energy output of the integrated energy output of your source. So it is a complicated nonlinear effect that happens at the source and then propagates out as a step. Now, from the perspective of particle physics and so on, that's hugely interesting. But even here, it's interesting because that step function means that you have energy at low frequencies. And so that is the thing that you can observe with LGWA. So you see here, these very high low frequency amplitudes this is the memory effect essentially produced at the source. And so you can detect this, and it's even much higher amplitude than, you know, what you get here at the peak at you know, at thousands of hertz. So strange enough, supernova type, you know, core collapse supernova might be easier to detect at low frequencies than at high frequencies, which is not really the story of the past. Okay. Now, a little bit about the instrumentation now. So, for us, there are like some risks that we have to manage when we now think about how to proceed. The first is our limited understanding of the geophysical environment on the lunar surface and the lunar interior. So these are so big question marks that no space agency would pay, you know, LGWA to go on the moon without knowing more. And so we proposed Soundcheck as our pathfinder mission, and it is a single seismic station that will be short-lived, like you know, a few months of data, deployed inside a permanently shadowed region on the moon. And so the goal here really is to measure magnetic fluctuations, temperature changes, and the seismic background to some sensitivity, which is now, you know, we are targeting essentially picometer per square root of hertz in the decihertz band. So that is for us the pathfinder, and it will not be so much a technological demonstration, also that, but it will be really essential to get a lot of new information about the geophysical and internal structure properties of the moon. And then, based on that data, we will be able to plan LGWA in detail. For example, you might ask yourself, yeah, you suggested to deploy an array of seismic stations on the moon. Yeah, but what has to be the distance between them? It turns out the distance has a meaning between the stations. You cannot have the distance too large because you don't want to make fully independent seismic measurements on the moon, but they can also not be too close because then it's essentially the same signal in 4 stations. So there's an optimum to distinguish between seismic backgrounds and gravitational wave signals. And this optimum distance is connected to properties of the seismic field. So, you know, you have to know that. Otherwise, you don't know exactly where to deploy your stations. But then, once you have done this, you can think about, you know, making this kind of configuration. And now here we are targeting, you know, close to femtometer or maybe even sub-femtometer per square root of hertz measurements on the moon. That would be LGWA. And to reach that, you need superconductors. You have to go to, if you don't find a superconductor, a good one that operates below 40 Kelvin, which is the ambient temperature, then you might have to cool it down further with a cryocooler, which of course should not introduce any vibrations. But in any case, so this is essentially the profile of LGWA, and we are targeting a 10 years measurement time on the moon. You might think, like, where does this number come from? Isn't it a little bit out of the blue? So it's not completely out of the blue, because all of the seismic stations of Apollo operated for years without problems. They survived the day-night cycles for many years. And then at the end, they were just switched off in '77, essentially. NASA decided, we don't want to look at this data anymore. It's just too expensive, or, you know, nobody is interested anymore. No, we switch it off. And so it was switched off. So from that experience, we believe that if you could make a setup similar to what they did for the Apollo seismometers, you could easily realize the 10-year mission lifetime on the lunar surface. Okay. Now, this is a little bit how that is going to look like. It's a gravitational wave detector, but it's a transducer. It's a compact thing, right? It's just measuring vibrations locally. So it's very compact. And so you have here essentially a 10 kilogram proof mass inside a very compact niobium block here. It's all monolithic, so yeah, there's no cutting and welding. It's essentially just creating here with internal cuts the structure so that this mass can move around. Then there will be a compact laser interferometer that will read out the displacement of this proof mass with respect to the frame. This has to be on a level, on a leveled platform, so it must be, like 10 microradian leveled platform. The tricky part here is it must operate in this 40 Kelvin environment, so not so easy. A cryocooler, two-stage sorption cooler, and so on and so forth. So this is like technically how that payload is going to look like. And we have, luckily, a European team, well, not only Europe, also a bit outside Europe, working on all of these components already at the moment. So we, for a terrestrial demonstrator, if you want. One example is a collaboration, for example, between Unicamerino, Max Planck Institute in Germany, and the NPL in India, where they are working on these superconducting actuators. So essentially, why do you need these actuators? Because you want to be able to push the proof mass of the seismometer. Because if you just let it like swing freely, it will not give you the most sensitive measurement of the displacement. You want to essentially force it to keep it at a certain location. And so then the signal that you need to keep it there will contain the gravitational wave signal, essentially. And so these superconducting coils are like thin film coils that you put on the materials. And so you push essentially with a Meissner effect against a superconducting material. So the magnetic field lines don't even enter the materials. You're just pushing, they're pushing around the proof mass and producing the force in this way. And so just recently, like end of last year, we saw a superconducting, transition into a superconducting state of niobium nitride with a transition, at a critical temperature around 14 Kelvin, which was important for us. So essentially, that structure could now be deployed on our seismometers and be used to actuate. What we are now trying is this higher, ideally above 40 Kelvin, because then we could just deploy it in the PSR, in the permanently shadowed region, and it would just work there in a superconducting state without need to cool down with a cryocooler. So this is the thing. We look at new materials to push this above 40 Kelvin, because that would greatly simplify our payload. Okay. Well, let me skip this part. This is about the leveling platform, which is something that we are also working on at GSSI. Important is, for sure, the expertise with the compact laser interferometers. Luckily, the field of gravitational wave detection has produced many experts around the world on this topic. We are working together with a group in Hamburg, really specialized to making these very sensitive compact laser interferometers that go to already now to 20 femtometer essentially in a laboratory. It was almost easy for them to demonstrate this kind of sensitivity. And so we have to get to femtometer, sub-femtometer to do this for LGWA. Then, something that we are doing at GSSI, at LNGS actually, because here's the missing link now, the last step that is missing. If you build a really good seismometer, now how do you make sure that it has the promised performance? So we are targeting like femtometer kind of sensitivities, but how can you tell people, look, we achieved femtometer sensitivities, bring it to the moon? Because that will be a requirement. You cannot just demonstrate like, a picometer sensitivity, send it to the moon, and without ever having verified that, that you can actually see gravitational waves with it. So the thing is that you need a facility where you can demonstrate on Earth femtometer sensitivity of your seismometers. And so this is what we call, Gemini, which is actually also part of an Einstein Telescope R&D project. But we will use the same facility. Essentially what it has is like 2 vacuum chambers connected by a pipe, so this is more the structure that's needed for Einstein Telescope. But then on one side, we will have also a cryocooler, and we have these suspended platforms. So these are 2 meter wide platforms, and then these are suspended and stabilized against vibration. So we have sensors on them to stabilize the displacement of these platforms with feedback control. And then we achieve essentially a picometer level vibration. Now on the platform, we will have now a cold box that simulates the temperature of the PSR. And inside the box, we will have two LGWA seismometers side by side at the right temperature. And now they will observe the picometer vibration from the table, that the residual vibration, and then we will subtract the signals from each other. And that will then, that's the idea, get us to the femtometer level demonstration of the sensitivity. And so this is the thing that we are following. Of course, we are profiting already from the fact that we are like deep underground, more than a kilometer. It's very, very quiet here in the decihertz band compared to other sites. And then we have full control over human disturbances, of course, and so on and so forth. And then we are hoping really here to achieve record values for vibrations of these platforms so that we can make the test. Yes, and I think we are coming close to the end. So here, this is just to show a little bit where we try to get from millihertz to hertz. These are the targeted sensitivities for LGWA sensors, for the Soundcheck sensor. Blue is essentially the residual vibration level that we attempt to achieve with Gemini on the platforms. And the red spectrum is the noise of the sensors that were deployed with Apollo on the moon. So you see, between Apollo to LGWA, we are talking about 4 orders of magnitude of improvement. That's really a huge step. Okay. Now, timeline, of course, scientists are never in control of the timelines. We can do our best in our laboratories and then convince space agencies, and then they will give us the timelines. Let me say the way to understand this plot here, or this diagram, a conceivable timeline, what we believe, what we can achieve on our side when we are ready with our technologies and when we think space agencies could take over and go forward with us. So essentially, on Earth, we are aiming for a demonstration of Soundcheck sensitivity on the Gemini platforms by 2028. So this is relatively easy to achieve because they are not so sensitive seismometers compared to LGWA at least. And so that is our target, 2028, essentially full demonstration of the integrated system at Gemini for Soundcheck. And then whatever space agencies tell us how much it takes to get to the moon. We hope early 2030s. LGWA payload, there's certainly some R&D that has to be done. It has already started. Then we have to also produce the integrated payload and the testing on Gemini platforms. And then we might have maybe LGWA data around 2040. I think when you talk to space agencies, they would think this is kind of optimistic, but that's our goal, okay? And you see, of course, LGWA would certainly observe in parallel with Einstein Telescope. If Einstein Telescope happens, that's maybe the one remaining question mark. And LISA, we don't really know, because LISA is supposed to launch 2035. It might have a 4-year lifetime. It is actually, they're trying to push it to more years, but it might end at 4 years. In that case, probably we will not have observations together with LISA, but okay, there's nothing we can do about it. And so last but not least, I just want to tell that, yeah, we are at this point really a big collaboration. We are now 16 institutions only working on the payload. So we have divided the payload up into components, and we have now 6 institutions working on the different components like electronics and all of that. And we have a science group forming and developing to push this project further. And yeah, hopefully, one day we'll see it happening. Would be great, but it's also a lot of work to be done still. And so here I want to stop. Thanks.
Working? Yes. Thank you, Jan. Are there some questions? We have time, a few minutes, so. Fabrizio?
Grazie. A couple of quick questions. First, what's the estimated cost for this experiment? And the second is more a curiosity. The installation of it would require manpower or person power on the moon, or we now have something that we didn't have in 70s that can install?
So, two excellent questions. So, in fact, let's start with the cost. We don't know for sure because there are some aspects of this which are really revolutionarily new, which is essentially the operation at cold temperature. So the industry has not a lot of experience with producing entire payloads, you know, including the lander and everything, to work with all the communications, everything at these temperatures. And so this is generally a challenge of, you know, anyone who wants to go to the PSRs to get the industry up to level. And that will increase the cost for sure. Whatever solutions the industry comes up with, it will increase cost compared to what we're used to. To give you a number, Chandrayaan-3 was a very successful mission of the Indian Space Agency. They deployed on the moon, they deployed a rover, they deployed a seismometer on ground, the rover went around, and the mission cost was $60 million, including the transport, not including personnel. So, 60 million. That's how cheap it can get. I mean, that's also a record, really, but it was really successful. And India is also planning already missions that go into the PSRs. The way they do it is they land outside the PSRs, and then the rover will go inside the PSRs. So LUPEX is this mission, for example. So with LUPEX, I'm curious to hear what the cost number will be, how much above 60 million it will be, but it will be above 60 million for sure. Nonetheless, here the payloads are really more massive. We are talking about payloads that you put on ground which are 50 kilos instead of, let's say, 5 kilos. So in terms of LGWA will for sure cost much more than, you know, these 60 million. So we are currently planning with, thinking, people who have experience with this, with Mars Insight, for example, they tell us, you should think about 500 million kind of number to realize that mission. But there are really big question marks. It can go either way because also the transport cost might still go down. So it's, it's a little bit, there are question marks, but $500 million, that's the one estimate. The other question was about, what was it again?
You need people on the moon.
Yeah, so, no. We could profit from people because it would be much easier to deploy the array. If you have like a central landing and then you just bring with human beings the stations in position, would be fantastic. But if you rely on it, of course, then things become very complicated. So, we hope that a rover can do the job. If you look at Mars Insight, there was a rover and then there was a robotic arm and it took like the payload and it put it on the ground. So you can do that. And so we hope that this kind of technology working at these 40 Kelvin environments would be possible so that we don't need human beings. But developing a rover that works at these cold temperatures with complex operation like a robotic arm and all of these things, that's not trivial. It's not in our hands even, right? So it's very complicated. We'll see.
Same question from Alessio. Other questions? Vladimir.
Thanks for this presentation. So you said that in the beginning this Apollo mission suffered because they didn't calculate the gravity and it was not tested. So how it should have been tested for the gravity and how do you plan to test it?
Yeah, so in their case it was a horizontal lever arm that kind of was supposed to make this kind of motion and then it couldn't be leveled. So they were supposed to put it on a slope so that you take off a little bit from the gravitational force along the lever and then you have less pulling down. So that was the idea. And yeah, that was proposed. So I think Joe Weber himself, he told them, look, don't we want to make this test on a slope? And then they said, no, no.
And then for you, the gravity will be a problem?
So it turns out that our system works a bit differently mechanically, and we are much less susceptible to gravity changes. So the impact on the G on our seismometer is not so much that we have to align it some special way, but that the natural frequency of our pendulum, if you want, in the structure changes. But you can adjust it because you know, the mechanical structure is what we call a spring anti-spring mechanism, where you essentially have an inverted pendulum and a pendulum acting together to create a very low resonance frequency in a compact object. And so it turns out that the frequency of that pendulum, this combination of pendulum and inverted pendulum, you can tune quite easily by moving a mass a little bit around in the center of the mass. And so that allows you to, you know, essentially, of course, you would recalculate the position of the mass so that you get the right frequency on the moon. But if it's not quite where you want to be, you could even imagine that there's some kind of motor that drives it at the right position later on.
Okay, thanks. Sorry, and last question, like this big mass that you said of 50 kilos is because like bigger mass gives you better precision, less noise, or because it's cryogenic system which is heavy?
So a lot of the mass, so by the way, Soundcheck is even heavier as a payload because we want to operate it with a battery. So I didn't really say much about the real problem of our mission, which is the survival in a PSR. Once you are out of sunlight, the question is, where do you get your energy? And so for Soundcheck, we want to survive 2 months, let's say, and we want to run on battery, which of course at this point has to be kept at the room temperature. But for LGWA, where we want to survive 10 years, there are only two ways. Or you have a nuclear power device, as was used in the Apollo missions. So they all had this RTG, which is essentially providing the energy, which is very good, but it needs plutonium. And so today, difficult. Or you could have solar cells outside the shadow and then beam with a laser or microwave inside the shadow and have a receiver there, or you have a cable. So these are essentially our ideas. For the payload, for LGWA, it's indeed the mechanical structure because we will have on each station 2 seismometers at the right angle to monitor displacements in 2 horizontal directions. And each block will have a mass of 15 kilograms. So we are already at 30 kilogram plus a little bit, you know. So that's how we get to the mass. And you need the 10 kilogram or, you know, each block 15 kilogram, the suspended mass 10 kilogram to reduce the thermal noise in your suspension. That's the same mechanism that we use in Virgo as well. Large mass helps with the thermal noise, yeah.
Yeah, another question. You insisted a lot on this 40 Kelvin environment temperature, but in the space is not an advantage because the problem is that there is no thermical conductivity from that. So if you have any device inside your module, you will not be able to cool them. And probably it doesn't make any difference if you are at room temperature or at 40K.
Exactly. So everything that produces energy will not be in the science payload. So what we will do is we will have electronics, laser, anything that dissipates on the lander. And then we have a wired connection to each station. And these are purely passive systems with no dissipation in the superconductors and maybe a tiny, tiny bit of dissipation of the laser that we use for the readout. So we need like some milliwatt of laser power. And of course, that gets absorbed there in the photodiode. So that is the heat input. And now we have, you know, people at University of Twente who actually tell us this is what you have to do to get this milliwatt out of your payload. Yeah, that's an important point.
Okay, I think we can close here. We thanks again Ian for the very nice talk and seminar for us. And now you are all invited to eat and drink something outside. Thank you. Nice to meet you.
Nice to meet you.